Hello, everyone. Welcome to the next episode of the Hewlett-Packard Lab podcast from Research to Reality. This time, we have a great pleasure to record it in Spring, nearby Houston, as a part of Hewlett-Packard Enterprise TechCon. And we've been doing it for many times, close to 150 or so, even more so. And the name of the podcast is From Research to Reality. Sometimes we spoke about research, other times we spoke about reality. This is the first time that I have outstanding pleasure and honor to host two people, Pedro Bruel, who will be talking about research.
Hi, Dan.
And Duncan Roth.
Hi, Dan.
Who is going to talk about reality. That is how we transfer Pedro's research into reality. So, can you tell us a little bit, introduce yourself? You've been here actually in many, many podcasts, but from the other side of camera. So can you tell us a little bit who you are, what you do in labs, then we go to Duncan, we go back and forth.
Yeah, hi, I'm Pedro. I work at the Heterogeneous Serverless Computing Group at the Software Architecture Lab in Dayan's group. I work with design space exploration and performance modeling and evaluation.
Okay, Duncan, how about you?
Hi, I'm Duncan Roth. I'm a HP fellow and I'm chief architect for Slingshot. So I'm on the business side. Our focus is on new product development and things that we're going to introduce into Slingshot products over the next 3, 4, 5 years.
Yeah.
Our research timescales are much longer than that, so we work with the team in labs on things that we're looking at and sort of medium to long term, and how we might introduce new technologies into our products in future.
And so, Pedro, I know you can't tell us everything what you do, but at some higher level, could you tell us, because you publish a lot, you even gave outstanding talk here at the TechCon. I was in love with it. I like your little animation. Can you tell us what you do for Duncan?
Right, okay, so part of the work that we do involves defining a design space of interest, especially to Duncan and to customers of that kind. And then we explore that space using different kinds of tools. We can use simulators, we can use different kinds of statistical models, such as the one in my presentation, where we represent how the model is capable of representing the data that we measure. And then that can feed back into the other business units and other consumers of that sort of simulation to gather insights and decide where to move next.
And Duncan, tell me, why is this important to you, what Pedro is doing? Why couldn't you do your work without it?
So let me give you an example of the sort of thing we want to do. We want to model a whole AI workflow. So not just one little component of the workflow, but the whole workflow, and to be able to ask what-if questions about that workflow. You know, what if I was able to make this element of it go faster? What if we were to change the model in this way? So in our team, we'll build simulations of individual components or of systems. But they're rarely a simulation. We can't simulate a whole workflow, especially something complex like an AI inference workflow. Mm-hmm. So that's the sort of project that we're interested in. How do we build this capability? What can we learn from it about what needs to be in our product in the future?
So what does it mean in practice? I mean, I heard you saying you're doing design space exploration. Describe it a little bit. But what do you give? What is that design? Is it a piece of paper? Is it a graph? Is it a song? What is it?
Well, it is a computer program which you can interact with, and you can define the limits of the parameters that you want to explore. And then the system is capable of giving you back other regions of that space where you might find interesting configurations depending on your need.
Yeah, but you describe me what it is. So you just have the program and you give it to Duncan and he's using this program, or you prepare some graphs for him? What do you do?
Well, in my view, it's always an interaction, so it's a loop.
Nice.
Duncan comes to me with a problem and with a target, such as the LLMs or collectives in the network, and then we bring back results and the graphs and experiments and suggestions of configurations. And then he can come back and bring a refinement of that initial space, and we can do that iteratively.
And so how does it look from your side? He just shared he seems to be happy. Are you also happy with what he gives you?
Well, we need to be able to model things which are much closer to our customer workflows. That's the real challenge for us, is that typically when you design a system and design a network for that system, you have to make assumptions about the traffic that it's going to that's going to flow, and how that system is going to be used. And what if it had a mixture of different workloads on it at the same time? How would it behave? But we also need to be able to do so. Those are sort of point simulations of the behaviors of devices. That's part of our normal flow. But we're not really able to look at the whole of a complex workflow that one of our customers might be able to do. So that's an example. It's an example where the output will tend to be a discussion and parameter space exploration, and these are the interesting possible solutions. There are other problems that we're looking at where the end result might be much more closely coupled with the hardware. It might eat something that might even end up being in the firmware, for example. So a range of different results.
And everything you do for Slingshot.
Yeah, I'm in a business unit.
Slingshot business.
And this is a piece of HPE-owned IP. It's something that came to HPE with the acquisition of Cray. And we're looking to broaden the use of that technology across HPE products. So we have to be able to study what the workload from those different products would be, how it would, what the advantages would be of running it on our current system, maybe, or what we might have to have in a future system in order to.
And I'm very interested both in present and future, but
Sure.
before we do that, let's dig a little bit deeper in the past.
Okay.
I just happen to know that you work in Quadrix.
Yeah,
So
yeah.
this is not the first time that you are dealing with interconnects. Tell us a little bit about it.
I worked in small parallel computer companies first. So after my PhD, I worked in a company called Mako. And then in Quadrix, which was a networking company that I worked in and ended up running. And then I made a sort of career change. Instead of stressful job running a small company, I switched to being an individual contributor building networks at Cray. So I came to HPE via the Cray acquisition.
To our happiness.
To
And Pedro, this is not the first time you're doing design space exploration. You've done it at least a few times before, didn't you? For your
Right.
thesis and elsewhere. Can you tell us a little bit about that?
Well, the most recent work that I did on that direction was during my postdoc, which I also did at HP Labs, but in a different group, on the Emerging Accelerators team. So they were interested there in a co-design problem between selecting and tuning trees, decision trees, to their specifically designed hardware, which involved analog content addressable memories. So the work I did there was also on design space exploration, but the loop was with the hardware designers and the software developers of that group, where, well, I was inserted in that loop as this sort of explorer of the space and suggester or maker of suggestions of places to explore and hardware configurations to try.
Very nice. So it's really interesting to be able to do it in different areas. Now, coming back to the present time, why Slingshot? Why is this customer's problem? Couldn't they just put Ethernet, InfiniBand, your choice, and shouldn't it just work, or what happens?
So what originally drove the development of Slingshot was to produce a interconnect for the US exascale systems. So those are very large systems. They're designed to run applications at the full scale of those systems. The machine, sometimes it'll just run one job on the whole machine. Because of the sheer scale of the machines, there are going to be lots of faults that you have to handle as part of, in order to get applications running for long enough on those systems. So you could build a cluster that's that size, but you wouldn't be able to run a tightly coupled parallel job on the scale of the machine and have it perform.
Why not?
Consider an application which has got millions of processes distributed over a parallel machine, and they're all communicating with each other. So if you want to, if you use conventional, let's say you use IP protocol, or you use socket communication, or you use InfiniBand RDMA, these are all called connected protocols. So you have state that connects you to every one of the other processes or nodes in the system. So you make the system bigger, and this state explodes, rises quadratically. They found out really in the early to mid 2000s that this was going to be a problem, and that you could build a machine but then you wouldn't be able to run a job on the whole machine because the memory consumption would be too high. So now scale up the machines from the sort of size that we were talking about then to the exascale machines, which have got tens of thousands of GPUs, and you're trying to use all those together. The memory requirements for what are called connected protocols are enormous. You wouldn't have any memory left to run the application. So we designed a set of connectionless protocols that use small amounts of memory on each of the nodes, and then we designed a way of making those things reliable. But you mentioned Ethernet. Couldn't we just use it with Ethernet? We did choose Ethernet as the physical media, and so we use Ethernet cables and connectors and IP in our components, and then we run Ethernet protocols. Some Ethernet protocols, but we also built a transport and a runtime for running large-scale HPC applications.
Very interesting. Thanks for that in-depth explanation. So to achieve this, how do you help him? Do you take it even to the next level? Do you further optimize resources? How do you do that? What's your secret sauce?
Well, as Duncan mentioned, these things are ideal for very large scale machines, which are very expensive, and you cannot build many of them in many different configurations. So one interesting thing that automated design space exploration methods could do is help the exploration of these different configurations of things that are very expensive. I refer back to the chip design work that we did, where you can always build less than one chip, but ideally you build one. And with the scale that Duncan is talking about, you can also build few systems of that. So automated methods of exploration and simulation are useful.
And you're very modest. You told me I do the program, but I actually saw you doing one simulator, second simulator, third simulator. Can you tell us a little bit about
No,
what
they
that
drive
is?
them hard in labs, you see. Dan works his staff 24 hours a day.
Well, there are different purposes for these different tools. So the first simulator that we tried was an analytical script that took the napkin calculations of something that we can quickly define, and then use that to try to push and try to prove that something is in concept, it's feasible. And then the next iteration of that, you can go and use things like the SST simulator that you can compose and then go a level deeper. So now let's model how the hardware actually works and how the components of the hardware connect. And then with that, we can get more into the actual performance measurements that we want, where with the first approach, it's more about trying to prove that it's possible or that something has a value that we can get.
I was going to say that we use simulation throughout the design process. So Dan and Pedro have been talking about applications that are quite a long way away from product, and then we're moving towards things which are much closer to ensuring that we get product out on time. For example, we need to be able to run before we commit to a manufacture fabrication of our ASICs. We want them to run realistic workloads, so things that are representative of how they're going to really be used. We want to do that as part of the design process. That's how we solve. That's how we ensure that we make good quality components, that they have low numbers of bugs. It helps us get our products to market quicker.
So let's move now to future. You just built exascale, even beyond exascale. I think the Next has over 2 exascale.
Yes, it does.
So you're going to go 100 exascale. You go to so how is Slingshot going to support all of that?
Okay, so the thing that we're doing at this moment is building systems which have both higher bandwidth and a broader range of function. So bandwidth is being driven by the explosion of use of GPUs. Okay, so the higher performance of GPU they put into a system, assuming your job needs to use more than one GPU, and large inference and training jobs, HPC jobs, need hundreds of GPUs. So now those GPUs have to communicate with each other, and you give them more higher and higher performance. So now they have to have, you have to increase the bandwidth between them. You want to try and achieve lower latency if you can. So we're pushing on the performance of these systems, but we're also pushing on the functionality. There's a stereotype of a Cray system in a bunker. Well, it's been a long time since you actually had to go and use the keyboard in a bunker, but they were built for say for numerical simulation applications, and you had to buy and install and run that system. Well, one of the things HPE wants to do is to provide supercomputing function as part of our cloud infrastructure, for example. You want to be able to have a slice of supercomputing resource, and perhaps not rent it, but lease it for a few months, or run particular applications on demand on that system. So that needs us to build new function into our networks. So we're kind of pushing on bandwidth and pushing on function. We could build systems to quite high scale. The target that people are aiming at next really is the 10 exaflop range. Hundreds of exaflops are way away, and I think there'd have to be some fundamental changes in technology that would improve the power consumption.
These systems grow so quickly you can't get used to the next level. But tell me another thing, Pedro. He keeps on building and building and building, or can your simulators catch up? Or are you having in your back pocket another simulator that can help you both simulate low-level switches, for example, and also the whole system? How do you go about it?
Yeah, I think, as Duncan mentioned, I believe the next step for simulation would be to be able to support the workloads that are the workloads for which there is interest in running in these kinds of systems. So being able to provide performance estimates of the systems running workloads at scales that you can't perhaps not even achieve. So this requires different sort of simulation, different sorts of analysis that you got to do. For example, you can replace components in the simulator that are harder to model and take a lot of effort and time to obtain a measurement. You can replace those with models of these operations, and then that would speed up the simulation itself and the design process as well.
Okay, great. Really insightful. So Duncan, tell me one thing. We started that conversation about Ethernet. Does it have to do anything with, because it's standard, underlying protocol, or why did you choose Ethernet? And how does Slingshot work with the rest of the world?
Okay. So historically, high-performance computing has used proprietary networks, and Cray built many generations of these networks. But over time, we came to the conclusion that it was a better plan to add the functionality that we needed to a high-volume network, something for which there's a huge ecosystem of components and IP that we could access, to add the function that we needed to that, rather than to keep building proprietary networks. So that's what drove us in the direction of using Ethernet. The Slingshot systems that we're shipping today have the first generation of a set of new function added to Ethernet to provide it with high-performance computing function. Now, what's going on in the wider industry is that people want to take the function necessary for AI primarily, HPC and AI generally, and provide that function on Ethernet networks so that you can both run AI training and inference, but also you can get data in and out from the data center, from input devices, from storage systems, and you can interact with other parts of the system, and also you can take components from different places that all interoperate because it's Ethernet. So this work's going on within an organization called the Ultra Ethernet Consortium. And so ideas that we developed and put into Slingshot are feeding into that. We're an active member of that. So that in future, we'll be able to take components from an accelerator vendor who, say, bought some NIC IP, or a storage system vendor who has UEC, Ultra Ethernet NICs, and they'll all be able to interoperate in an HPE system. So that'll bring the things that we do into the standard world, and then the Slingshot team will focus on really high quality implementations of those standards.
Great explanation. Let's flip the coin a little bit. Our company takes pride of doing for the broader good. How does work that you and Duncan help the world?
Okay, so one of the main areas where supercomputer systems are used is in the weather forecast community, the climate research community. They've been using these systems for many years. They were always good customers of Cray, and so one of the biggest deployments of HPE's supercomputer systems in the UK, where I come from, is with the UK Met Office, so one of our local weather forecast agency, and they have a big cloud infrastructure to run all their sort of production applications, and then they have HPE Cray supercomputers sitting behind that, producing the numerical forecast data.
Great explanation. So, Pedro, Duncan works with customers, works with standard bodies. Are you engaged with any professional organizations such as ACM, IEEE, and how do you work with them?
Well, I am a member of both the IEEE and the ACM, and one example of engagement is that we often record live transmissions for the IEEE industry hub in Silicon Valley. So
nice.
That's sort of
thank you for doing that.
One kind of engagement.
But do you also publish papers?
Of course, we publish papers, we go to conferences, we serve as reviewers and program committee members. I do that in the supercomputing workshops, and I do that for workshops that happen inside supercomputing as well.
And Duncan, he's publishing papers. Are you doing patents, and how are they important for what you do? Okay,
so patenting our IP is very important at HPE, and the company runs a scheme where anyone who who invents new technology, new processes, new algorithms, new techniques. They write a disclosure of their invention. And that's quite a straightforward thing to do. People are sometimes put off by the complexity of filing patents. Well, you don't have to write the patent here. In fact, we would not let you write the patent here. What you do is you describe your invention in an IP disclosure. And then that goes through a review process. And if it's accepted for filing, then a specialist IP attorney will work with you to create the patent. So it's a good process and a lightweight one. You can get into this quickly. There are incentives for people to do this. And then if you get to the point where the patent is written and they're going to file the application, you have to put in a bit more effort at that time to review the drafts. So the company encourages this, and the Slingshot team patents heavily. We do this because the area that we're working in is one where lots of other companies are all getting interested in AI networking. And AI networking, HPC networking, they're very similar things. So it's important to patent almost all of our ideas.
Thank you for explanation. We like to end on a personal note. You just arrived here a few days ago from
Sure.
UK. You spent Christmas time with your family in Brazil.
Yes.
And now all three of us are here in the middle of the Texas. How do you see the differences where you grew up and lived and you are at the moment or where you live now?
Well, one difference is the food. Brazilian food is very particular in the presence of certain kinds of barbecue and certain ways of making it, and we don't really find it in a lot of places in the US. So food is an aspect that is close to heart and very important for Brazilian culture.
How about you, Duncan?
So I'm based in Bristol in the UK. I've lived and worked. My whole career has been based there, and we have an interesting office that's people from a combination of different parts of HPE who work together in that office in Bristol. So I'm here in Texas for the week. It's a good week of the year to be visiting Houston. It's nice. But mostly we're here to meet our peers, to meet people who've succeeded in getting papers into TechCon, or people have been invited to TechCon.
And occasionally to record a podcast.
Apparently so, yes.
If you could do one thing differently in your career, what would that be?
Well, with the benefit of hindsight, I think I would have gone towards computer science or computer engineering earlier in my career. My first undergraduate research project was actually in the sequencing of the genome of sugarcane.
Oh, nice.
So I worked at a lab for 6 months. I was able to withstand working in an actual biological lab, and I grew bacteria, extracted DNA. I learned a lot, but I think that what I like the most is computer science, computer engineering. So.
And Slingshot.
And Slingshot. But without having explored, perhaps I wouldn't have figured that out.
Yeah. And Duncan, you had many turns, and
Sure.
which one you would have not taken in the hindsight?
Well, quite early in my career, there was a point, just as we were starting Quadrix, in fact, where we could have taken a slightly different turn and pursued a startup of our own at that point. We didn't do that at that point, so things could have worked out very differently if the group of people that I was working with at that time, because we'd come from one small startup, Mako, we were thinking, did we want another one? So these are people who are these days are spread out around lots of US tech companies. So sometimes I wonder about that. My PhD was in theoretical physics. I couldn't have continued doing that, so I'm pretty glad I changed from that to parallel computing. But,
Good choice.
Yeah,
Good
I think
choice.
so.
Any book to recommend to our audience?
Well, I've recently read a book from Nick Lane called Transformer. It's about not about AI transformers, but about the transformer that we all have in our bodies, the cells. So it's a book about the cycle of Krebs and how it fuels both life and death. So it's a book about a science communication book about biology.
Nice. Duncan, you?
Oh, what have I been reading recently? I tend to pick reading material to relax and not think about it too much. So maybe I've been. I guess I was reading some LA detective novels recently.
Nice, nice.
So that's a good thing to do. Who knows what it'll be next week? But something very different from work.
Okay, gentlemen, thank you very much.
Thank
Lots
you,
of
Dave.
good information.
Thanks, Sam.